So the plan is to give a talk about this software and how can you use this. So this will be a very, say, naive presentation showing somehow the basic stuff that you can do. And at some moment, I will try to state some exercises, say, that hopefully we will be able to solve during the week. And also how you can use this software, not only for teaching or for playing, but for doing some kind of research, right? So in non-commutative algebra. I don't know if you are interested in non-commutative algebra, but I will just state an interesting problem, which is open, and how can you play a little bit with this problem. Not solving this, but well, at least to have a feeling of what is going on, okay? So it was working before, but now it's not.
Oh, do you have to switch from the hand to the...
Okay, it's not. Okay, so first of all, this software is free, and it's open source. You can get it from this page. There you will also find packages, manuals, I don't know, presentations, books, several things. Okay, it's mainly for work with discrete algebra. You can work with it's mainly for working with groups, but you can also work with graphs, vector spaces, matrices, fields, rings. I don't know, several things. Okay, so this is the outline of what we are going to do here. We are going to play a little bit with very, very basic arithmetic. Then, well, the idea is to try to do some basic programming, then some linear algebra at a very naive and elementary level. Then, well, of course, elementary group theory, meaning, for example, that you can something that you can use when you are teaching, like I don't know, abstract algebra or something like this. And then we are going to move to some more advanced topics, like group theory, but, well, in a more advanced level, including, for example, representation theory of finite groups. We will also play a little bit with infinite groups. And then some application far from algebra, say, in some sense. If time permits, then we are going to do, for example, applications in combinatorial knot theory, or in non-commutative algebra. Okay, so this is more or less what I'm planning to do this week. Good. So let's start. So you need GAP to be installed in your computer, of course, and then you need to run GAP. Okay. Once you run GAP, you will see this prompt, this command line, and this is how you quit. So I will show you. I don't know if shall I share this? Yes, right? Okay, let me share this other window. Okay, so this is what you see when GAP is running in your computer, and of course you can just quit doing this. So the first thing important is that you have this semicolon again. Every line should end with a semicolon. Let's run GAP again. Okay. Very good. So this is important. And if you don't want to see the output, because maybe you need to print something which is very big, like a big matrix or, I don't know, a big list, maybe it's kind of annoying to see all the output. So instead of using one semicolon, you can use two, and then the output will not appear. Okay. For example, if you do this, 2 plus 5, well, you see the 7, but if you put a double semicolon, then you will not see this. Okay. This seems to be a silly thing, but it is important if you want to use it. Okay. And okay. So first important thing that it's very, very useful is, well, how to ask for help. In general, if you want to ask for help, then you need to start with this question mark, and then something that you want to learn about. For example, if you want to know how GAP works with sets, then you just write sets like this. If you want some information or some help about the helping system in GAP, well, this is what you do. If you want to know a little bit about permutations in GAP, well, do this. And Yes, this is like a general help. This is very concrete help. What we are doing here is to ask for help about this particular function of that Sylow subgroup, which of course returns the Sylow subgroup of your group. Or this one is to construct a free group, or this is to construct a cyclic group, or this is to compute eigenvalues of a matrix. Okay, this is how it works. So maybe I can just show you a little bit. Yes, I need to maybe share this because otherwise. So I don't know. Just let's try to see something. For example, I don't know, normal a subgroup. So I just put this, and I'm going to see what God can tell me about subgroup, about this function. You see that there are a lot of things here. Okay, so I need to choose one. I believe that the one I want is the first one, right? Because it says reference subgroup. All the others are very concrete and particular things that I don't want to see now. So I just, nothing is happening. It's just a list of comments and examples. But it's just to show you how this help system works. In this particular case, what I did was to ask for information about this function subgroup, and here it tells you how it works. Okay, you need some parameters, and then you can do something. And here you have an example. Fractions, okay, or this crazy operation here. This is how you get with this function. This is how you get the numerator of a rational number, and with this one you get the denominator. Okay, this is just nothing but what this is. There is a function to return to get this denominator. Okay.
Does it reduce the lowest terms first? Suppose you entered 6 over.
Yes. This is what it's doing. Yeah. If you put like this, we can do this experiment here. For example, if you put the
6 over 10
numerator right 6 over 10, you will get 3. Even if you write 6 over 10, then you will see this like this. Okay. Very good. So of course, another thing, another easy and useful command is, well, how to get a remainder. This is just using mod. And this is not a function. This is just a call, like an operation. Okay, it doesn't have uppercase letters. It's just it's an operation. It's working as an operation. Right? So this is how you get 6 mod 4 and minus 6 mod 5. Okay. But it's useful, of course. Good. So, and then of course you have several functions for very, very particular purposes. Like, for example, factors will return the factorization of an integer. But maybe if you just apply the same function to a polynomial, you will get the factorization of a polynomial, or who knows. Is prime, for example, detects whether an integer is prime or not. And here we have some experiments, right? Factors of 10 will return this, 2 and 5. And why the brackets, the square brackets? Well, because this is a list, okay? It's like a sequence of things, ordered sequence of things. Then we get the factors of 18. We check whether this number is a prime number or not, and then here the same, okay? Right? Very good. So good. So other useful functions. I'm just playing with some functions and some basic stuff, right? So SQRT, of course, is for computing square roots. Factorial computes the factorial of a positive number. You can compute, for example, the greatest common divisor or the least common multiple. I and you see some examples there. So here is you see something interesting. First of all, that well, it's quite powerful, but this is not surprising. But then you can compute, for example, the GCD of these two numbers, putting it this way. But also you can do this for more than two numbers. And in this case, well, you just do this. Okay? So this function is clever enough to be able to recognize the input, right? And to distinguish between different ways of getting an input. Good. So do you want me to put the terminal and make some experiments, particular experiment? Yes.
I want to know how to see all options of functions available by in the
Oh, well, there is a manual
Yeah.
with 1,000 pages maybe, and at the end you have like an index with all the functions, or not all, but almost all the functions.
So is there like a command that will actually like prompt that one out?
I think no. I don't know, but I would say no because it's really huge.
So where can I find that manual?
Oh, in the web page, or if you install GAP in your computer, then if there is some folder called documentation or doc or something like this, and the manual is there. At least some small version of the manual, but it is available in the web page of GAP. But in general, you will see that something which is kind of useful, right? So say that I want to compute the factorial. What is what I'm going to try? Just factorial, and I find it. Okay, say that I want to compute the Frattini subgroup of a group. I just try Frattini, and at the end I get the command, right? So it's not hard to guess which is the name of the function. In particular, because they are following some kind of rules. Okay, so we will guess somehow what is going on.
Is there a way to just, if you know first few letters?
Yeah, then you press tab. Yeah, you press tab and it works. So, for example, which kind of experiment do you want to make, or we leave this for later as you wish?
Well, I'm playing with it right now, and the square root function is giving some very strange results for non-perfect squares.
Yes. 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 I don't know what it's doing, but this is maybe explaining the documentation.
Okay.
Yeah.
It looks almost like it's doing something with roots of unity.
Yeah, I think so. Yeah. It's just doing something with cyclotomic integers, but I don't know what. Or maybe I knew something. Okay. So, for example, let's say that we want to work with cyclotomic fields. So, to create a cyclotomic field, this is what you use, CF. Okay? And you can create primitive roots of 1, for example, and the function uses this letter, capital E. So it means that this is a reserved word. You cannot use capital E for a variable or for a new function, because this is precisely the function you need to use to return a primitive root of 1. So for example, let's check this. Rationals is, of course, the field of rational numbers. So is it true that this primitive 6 of root of unity belongs to the rationals? Of course not. And this is what we are checking here. Okay? So you see that this command makes sense. Okay? But of course, this is a cyclotomic integer. And well, we can play a little bit like this. So this primitive third root of unity does not belong to this, but belongs to this. And you can, of course, play with roots of unity, right? In the way you want. I don't know what this is. I need to fix this. Okay. So what I'm saying here is that this is the same as this for GAP. Okay, and this is a type. Sorry. Okay. Why you write this like this? Well, because cyclotomic numbers will be represented as a rational linear combination of primitive roots. Okay. Okay. So of course you can compute the inverse of an element, say additive inverse of multiplicative inverse, and the function is just like this, right? If you just don't write multiplicative, then you write inverse, it understands that you want the multiplicative inverse. And if you want the additive inverse, just add additive on the name of the function, and that's it. And I have some examples here, right? So the additive inverse of the two-thirds is this, of course. The inverse is this. The additive inverse of this guy, of course, is this. And the inverse of this is just this. It's clear, right? Yes?
Should we write the minus exactly the same way as, first letter should be capitals and.
The first letter, yes, yes. This is like the convention. Yes, yes. You cannot change that, and this is somehow the convention, right? So the inverse is a function, so the first letter is capital. But then you have like a different version, say, of the inverse for additive numbers, and then you add additive at the beginning, again with capital and again with capital.
So if we write all of us in small letters, then.
No, it will not work because it's a different function. If you write additive with the lowercase a, then it is not the same, and it will not recognize the function. Okay. Good.
I have a question.
Yes, sure.
If you want to find the multiplicative inverse of 2 into that, then how do you need to specify the thing that you're the ring that you're looking at?
No, it will. I mean, so first of all, yes. So you have like a different ring, right? With this set mod 2.
Yeah.
This is something different, and the element 2 there is not the same as in rationals or in integers, right? So you have a way of representing this element. Right? We will see this later in 5 minutes. But you will have a way of representing 2 inside set mod 2. And then if you try to compute the inverse of this, you will get a problem, right? Because this element is not inverted. You get an error. Do you want to see this?
Yeah.
Okay. Let's see this. I'm going to share this because, okay, what is this? This is nothing. Sorry. But okay. I'm not very good with this system. Okay, so can you see this, York? He left.
No, he's just muted.
Okay. So not end set. I think that this is my ring, okay, which is of course a field. So this ring is the same as the Galois field with 2 elements. But so, for example, I'm just doing something. Let's see which elements do I have there. I have these elements. I will explain this later, but essentially I have the 0 and the 1. Okay? I will explain this in 10 minutes. Okay. So this is the element set mod n set how is this object. This is how you get an element inside this ring. Okay. Let's see the help. You see? So you can use, for example, this version R and N. So okay, this is the element R inside set mod N. Okay. So you want, is it okay?
Yes.
So for example, you can do something like this, 2, 2, and of course you get 0, right? And let's try to compute the inverse, and you will find the problem because this element is not inverted, and you get a fail. Okay. You can. But if you do this for the 1, of course you get 1. Is it okay? But you see, this is another very, very tricky and important point. Because 2, I'm saving the log file for this. So then I will share this because you can just recover all the experiments with it. So this is something very, very important, right? Because when we are writing mathematics, of course, 2 is 2. And if 2 lives in I don't know, in set mod 2, it's okay. But here it will not work like this because you see. This is not how things are, okay? Okay? And this is even more complicated. And if you are writing programs and your program is not working, there's a big chance to make this mistake, to think that the 0 here is this 0, which is not, because this is a rational number or an integer, and this is not. This is completely unrelated. Okay? This is a tricky thing that it is good to know now. Okay? So I'm going to go back to the to this. Good. So this is an exercise that I would like to solve during the week. I mean, it's not very hard, but I find it extremely interesting. Do you know this language, this programming language invented by Conway? So it's super funny. This is the name because it looks like Fortran. It was some kind of joke. And this is how it works. So a program is just an ordered list of positive rationals together with an initial positive integer. Okay, let's say n. The program does the following. So you need to update n with these two rules. Very, very simple rules. The first rational in the list for which n times f is an integer. Okay? For the first rational f in the list for which n times f is an integer, you replace n by an f. And you repeat this rule until no rational in the list produces an integer when multiplied by n. Okay? So it's this is an exercise that I would like to solve during this week. Okay? Of course, I mean, if you know how to write computer programs, then this is not hard. But if you don't know how to do this, okay, then, well, this is an interesting exercise. And of course, it is interesting to try to write this in Gap, right? Maybe you can do this in a different language, like Python or C or whatever. But, well, we are going to do this in Gap. Why this is interesting? Why I choose this? So I don't know if some of I know. Let me know when I can just switch the slide, because is it okay? Oh. So let me see. Okay, this. So let's say that I start with n equals 2. Remember that a program was just a list of rational numbers, right? With this n. So I pick this list, this crazy list of rational numbers. Okay, with this list and this particular n, I can produce this sequence. Okay, I mean, you can do this by hand, or you can just write solve the exercise and then test this. You produce this list. What's funny about this, and this was proved by Conway, is that this sequence contains this set. This is super nice, right? 2 to the p, where p is a prime number for all primes. I found this quite interesting. Okay.
How are these rational number chosen?
I don't know. You have to be Conway. If you want to see a little bit more about this, well, this is the sequence. You know the encyclopedia of sequences, right? This is the code for the sequence if you want to do more. So this is one of the exercises I would like to be able to solve. This is, I would say, not really mathematical. It's an exercise in basic programming, but I think it is interesting. Okay. Very good. And then I have another exercise, again Conway, and this is the famous look and say sequence. So can you guess the pattern here? This is the first exercise. Well, with the name, of course, it's easy, right? It's look and say. I start with 1, and then I see 1, number 1. Then I see 2 numbers 1. Then I see 1, number 2, and 1, number 1. Okay, that's pretty nice. Again, Conway, clever guy. And then I see 1, 1, 1, 2. Okay, 1, 1, 1, 2, and 2 1s. Okay, and I continue this way. And the exercise is, of course, well, after guessing how each term is computed, which is something that I did, you need to write a script to create the first terms of the sequence. Okay, this is the exercise. Again, there is almost no mathematics behind this, but it's an exercise interesting exercise in basic, super basic computer programming. Okay, so the idea is to review all the basic stuff. You need to write an efficient program to do this. Okay, this is something that we are going to do, I think, tomorrow. I'm trying to sell the second lecture. Okay, good. Okay, as I said, to solve this, we need some basic programming. Okay. What is what we need? Well, we need to know a little bit about conditionals, functions, strings, right? Lists, range, sets, records, loops. All these basic things that you are going to know about. So, for example, sequences are lists, okay? But a list is more than a sequence, right? Because inside each element of a list is not a number, maybe. It could be a number, could be a group, a matrix, a permutation. It can be, the first element could be a permutation, the second a matrix, and then numbers, and then nothing. I mean, it's really, you have a lot of freedom to define lists. What is a string? It's just a list made of characters. So it's different, okay? It's a very particular type of list. What is this? Well, it is a list going from one number to another, right? Ascending or descending, but it's this. What is a set? Which is the difference between a set and a list? Well, in a set, you have no repetitions, right? For example, right? This is a key difference. And let's say that you want to, I don't know, but say that you want to use the computer for doing something, for doing research. Then you have something that you want to codify and to understand and to work with. So the idea is to try to define an object, codifying all the things you want, right? How can you put all this information in GAP? Well, GAP is not object-oriented programming, an object-oriented programming language, but it's quite close because you can pack everything inside something, which is called a record. Okay. What is this? It's just a package. It's just a thing that contains all the things, and then you can access to all the things. We are going to do something like we are going to use this and to try to start making our own package for doing something. Okay. But of course, we will start tomorrow with this, not today, because this is kind of maybe boring. I don't know. Okay, so what I want to do today is first to do some basic mathematical objects in GAP. So I just to talk about three things: permutations, finite fields, and matrices. Why? I don't know. I mean, I want to use groups maybe later, or more complicated stuff later. And this was, I think it is a good starting point. Okay. And mathematical in some sense. So let's start with permutation. Okay, you know that a permutation in n letters is a bijective path from this set into this set. Okay. Typically, you use this notation, right? So this is the domain. 1 goes to 3, 2 goes to 1, 3 goes to 2, and 4 goes to 4. Okay. So this is the notation you typically use for functions, right? Well, you know that every permutation can be written as a product of disjoint cycles, right? For example, so this is So you know that 2 is connected to 1, 1 is connected to 2, 2 is connected to 4, 3 is connected to 1, and 4 is connected to 3. So you have one cycle. All these numbers are connected. And here, well, you have 1 is connected to 2 and 2 to 1, which is a connected component of the graph. Then you have 3 to 4 and 4 to 3. You have another connected component, and 5 is a fixed point. So this is the permutation written as a product of disjoint cycles. And the convention is that you don't write this fixed point. And if you do this, then you have like a change of inclusion in the symmetric group, say Sn, into the symmetric group Sn plus 1, and so on, right? So, how you write this permutation in GAP? Well, first of all, you need to convert this into a product of disjoint cycles. which is essentially unique, right? I mean, up to the order of commuting permutations and this fixed point is unique. And well, you write like this, precisely in the same way, right? The only difference is that you need to put a comma here. And you don't need to put the product here because it is okay. But remember this, for gap, this is not a point. This is a permutation, okay? And the permutation lives where? Where does this guy live? It lives in this one, okay?
In every Sn where n is a G-score.
Exactly, okay? So if you just test this, let's go back to this. Well, I will do this later, but we are going to test that this belongs to S4, S5, and I don't know, 100. But not this in S3, of course. Okay? So, for example, you have a function to test if something is a permutation. Okay? So, for example, if you just do this guy, is perm returns true because this guy is a permutation. Okay? So also you can check that this is the same as this. Okay? Again, gap is clever enough to know where this guy belongs, but to represent all symmetric groups in a way that you can embed one into the next one. This is very useful when you are programming, right? Very, very useful. Of course, you can think that this guy belongs to S4 and this to S5, and these are different things. But this is not really clever from the practical point of view. That's why gap is doing this. Of course, as I said before, it doesn't matter how to write these factors because they commute. So this is the same as this. It returns true. And then, well, is this a permutation? A permutation? Of course not. This is 25. It's a 25. It's a number. It's an integer. It's not a permutation. And this is also not a permutation. Of course, you can think that this is a permutation, but it is not. It's just a list of numbers. Okay? I mean, it doesn't matter if you can find a good interpretation where this guy is permutation. For gap, it is not. Okay? So, how to work with permutations? This is important. So the image of an element I under the natural right action, so this is important. Permutations are acting on the right in gap. In Argentina, we always act on the left. I think in Europe it's the same, right? Which is maybe not a good idea. It's better if things are on the right because you have this exponential notation. But this is the way it is. But for gap will always act on the right. In particular, permutation will be acting on the right. Okay? So I to the p is p, so it's the value you get after applying p, the permutation p to I, right? And of course, you can also compute the pre-image with this bar, this slash, backslash. Okay? So this permutation, 1 goes to 2, 2 goes to 3, 3 goes to 1. This is what we were doing before, right? This is how we read the permutation. Is it clear? Of course, this is a convention, right? But if you are clever enough when you choose the convention, then multiplying permutation is very, very easy. So we are doing this convention. 1 goes to 2, 2 goes to 3, 3 goes to 1. So what is this? Well, 2 goes to 3, right? And the pre-image, of course, is 1, right? Because, well, the guy that sends, that gets 2 after applying the permutation is 1. Okay? Very good. So, and composition is from left to right. It's different from what we do for functions, at least in Buenos Aires. Okay? So let's say that I want to compute this. Well, this is the same as this. And this is how I did it in gap, right? So this times this is this, from left to right. So first I apply this and then this. Not as you do typically with functions in I don't know, in calculus, okay? But remember, we are acting on the right. That's why, right? The first guy you apply is this, and then you apply this. Okay? But this is not so bad. I mean, it's okay. well, we are testing this here, and of course, you remember that you were able to compute the inverse of a multiplicative number, say using inverse. Well, this of course will work for permutations because these are invertible functions, right? And then if you just apply the function inverse to a permutation, you will get the inverse permutation, right? And if you apply the function inverse to an invertible matrix, you will get the inverse of this matrix, right? Which is, of course, the same as doing this, as you might expect. So several things which are somehow natural, well, will work. Not all of them, but some things will work. Okay? Very good. So let's play a little bit with permutations. So suppose that you have your permutation written as a product of its joint cycles. Okay? Well, you can make out a list out of this permutation using this function, list perm. I always confuse this and the inverse of this, but in general, names are well chosen. Maybe not this one, but okay. So it returns a list where you have this guy at this position. Okay. So for example, this is the transposition 1, 2. 1 goes to 2, 2 goes to 1. If I do this, list perm, I get this, which means that in position 1 I have a 2, and in position 2 I have a 1. Okay. Implicitly, what I'm thinking is that this guy belongs to S2, the symmetric group in 2 letters. But maybe I want to think that this guy belongs to a bigger symmetric group. Well, I just put the n here, the number of letters that I have here. If I do list perm this with this, what I'm thinking is that this permutation belongs to the symmetric group S4. So, okay, 1 goes to 2, in position 1 I put a 2, 2 goes to 1, 3 goes to 3, and 4 goes to 4. In position 4 I have a 4. Okay? So, for example, this, how can I understand this? Well, 1 goes to 2, so it means position 1 I have 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, and 5 goes to 4. And here, well, another example, okay? This is also very, very useful. And at the end of the week, we are going to try to write some application, and we are going to use these functions a lot. Very good. So, and of course, you have like the inverse function, right? So how to get a permutation from this list. Okay. So remember, this list is not a permutation, but if you want to make a permutation out of it, well, this is the function you need to use. If you interpret that, if you think that this guy sent 1 to 1, 2 to 2, and 3 to 3, of course it's a permutation, right? It's a function, it's the identity function, a particular identity function, right? So you get this identity. This is the identity. Okay. This is how God writes the identity in the symmetric group. And if you do this, okay, 1 goes to 2, 2 goes to 1, well, this is transposition, right? Is it okay? Of course, well, you know this very nice invariant of permutation in the sign, right? So you can define the sign, for example, as -1 to the k, where k is the number of transposition that you have in some factorization of your permutation as a product of transpositions, right? Very good. Well, to compute the sign, you just use this function, sign perm. And well, this is, okay, 1 minus 1. I have several examples, okay? Is it clear? Well, an exercise on permutations. So for a given n, you need to construct this particular permutation given by this expression. So n is fixed, and for each j, this is what the permutation is doing. And then you need to write your sigma as a product of these joint cycles and compute its sign. Okay, it's not a hard exercise, but well, you need to know a little bit of God programming in order to write this exercise. Do you want to make some experiments with permutation? Like what, for example? How is this? Let me see. This is my. Okay. For example, the first one is, let's write this permutation, okay? And let's check if this belongs to the symmetric group S3. So, to create the symmetric group S3, I use this function, symmetric group S3. This is a group, okay? And I'm testing if whether this particular permutation belongs to this particular group. Of course, implicitly, I'm assuming that the representation that I get here is precisely the one that I'm using there, right? But okay, it is. But this will not work, of course, right? Because, well, this guy is not. But what if I put here a 13, it will, right? Yes?
Let's say you created this 1, 2, 3, 4, and you want to refer to it in later days without actually having to even type this object over and over again. Is there a way to do it?
I'm sorry, I didn't understand.
Like you mentioned that this is very similar to OOP, like object-oriented programming. So can you just create like an object called 1, 2, 3, 4, so you can always refer to the name of this object, so you don't need to recreate it every time you use it?
I think so, yeah, but I don't know if it is convenient. But yes, in principle, of course, you can.
Right.
So yeah, in principle, you can create something and then try to, yeah, sure.
Yeah, just very long, right now, like to type everything.
Yeah.
You just need to store it in a variable, right?
Yeah, so like, yeah, you define it as like a variable and then.
Yes. This is, of course. I thought that you were talking about something more complicated. Like, yeah, sure, you can. Yes, of course. Yeah. So let's say that the P is my permutation. Okay, like this. You mean this?
Yeah.
Yeah, and then I can just say P belongs to the symmetric group S4. Okay, and then does it belong to the dihedral group? Say, I don't know, 8? Of course not. I mean, maybe in some particular representation you can find this permutation here, but not in general. Okay, I mean, these are completely different things.
Is the dihedral group?
This is a good question, but we can check this.
Subgroup or a symmetric group? Or?
Sorry, this is dihedral group 8 is the dihedral group with 8 elements. Okay, this is how the function works.
But is it like presented in terms of generators and relations, or is it just as a concrete?
No, if you write this, it has a very particular presentation, useful for calculation, but not as a permutation group. So, for example, let's say dihedral group 6, and I will show you the elements of this group. Okay, so I will just, instead of returning the group as a gap object, I will just print the list of elements. Okay, so this is what you see, nothing. Okay, impossible to work with this. So it means that you have 2 generators, F1 and F2, and then you have these elements. That's it. Not elements. You cannot work with this. But if you want to work with this, well, you can just this group, I think. I don't remember, but you put some kind of parameter in the function dihedral that return this as a permutation group. Maybe this will work. Indeed, it works. Okay. And well, it writes the dihedral group as a permutation group using some particular representation, permutation representation, which in this particular case turns out to be, well, the presentation of the symmetric group as 3, right? But this is something that GAP is doing and not asking how to do. Okay, so maybe, so what you're asking here is to return the dihedral group as a permutation group. He will choose or it will choose the representation. Okay, you cannot control which representation it is going to use. Okay, which other okay, let's say that if you write this 1, 2, 2, 3, 2, 4. Sorry. If you write this is not a product of disjoint cycles. This will not work. Okay. And this is precisely what it's saying. Okay. It says that, well, these are not disjoint cycles.
But you could put stars.
Yeah, you need to write as a product of these two permutations. Okay? This is a product of two permutations. This is just a mistake. Okay? Do you want to try another experiment or not?
Sure.
Which one?
Oh, I thought you had an experiment.
They have an audience.
Is there a way to like put an expression in instead of just a number? Like say you wanted to do a permutation that shifts everything to the right. Can you write like n and n plus 1?
Yes, sure. Yes. Maybe we will see this tomorrow. You need like inline functions, and then you can do this. Yes, sure. Very good. So let's go back to this. Okay. So finite fields. This also could be interesting. So you know that every finite field has p to the something elements, right? A power of p elements. So p is a prime number. So to create a finite field, you use GF, Galois field. This is the function. So of course, the characteristic of a field can be computed with this function, characteristic. And here you are using capital C, okay? So this is the field with 2 elements. This is the field with 9 elements, okay? The rationals, of course, form a field, and the characteristic is 0, you know that. This has characteristic 3, characteristic, this is a C, not a G, okay? The cyclotomic field, this particular extension, has characteristic 0. It's rational with a cubic root of 1, right? It's not a G, it's a Z. The same happens here. This is a G, so characteristic is 2, and this is a G, so characteristic is 3. Okay? Is it okay? Very good. And okay, how GAP will work with finite fields? So the key thing is the following. So let's say that F is our field with Q elements. Q is p to the n. Well, you know that all non-zero elements form a cyclic group with Q minus 1 elements. Okay? This is a well-known fact. So since this is cyclic, this is generated by some element, say Z. Okay? So F is what? Well, you have the 0 and then powers of this generator. Okay? So this is precisely F. So each non-zero element of F is a power of this particular generator. This is clear, right? Well, this is how GAP will describe a finite field. So GF4, of course, has 4 elements. Okay? Which are the elements of this? We use the function elements. Okay? Which are the elements of the Galois field with 4 elements? You have the 0, which is written as 0 times the generator. Or some generator. Because again, GAP is clever enough to know that the field with 2 elements will be contained in the field with 4 elements. Okay, so he's just using the smallest possible 0, right? In a clever way. The same happens with the 1. This generator of GF2, which belongs to this, is included here. Well, is the 1, right? To the 0. And then you have the generator, the proper generator of GF4, which is this, and then a power of this. Okay? So you see, why you don't see Z to the 4? Well, because this is the same as this. Okay, for GAP. And which is the inverse of this guy? Multiplicative inverse, right? The inverse of this guy, this generator, is precisely this, you know, right? Yes?
But there are a number of primitive roots in F, right? So how do you know which one it's picking?
You don't know.
It doesn't matter?
Yeah, it doesn't matter, yeah. But he's choosing one, and then he has some way of multiplying and adding, and that's it. This is all what you need. Say that you want to so of course not in this case, but say that you have a prime number of elements. right? In this case, you can have some more information. I will show you this maybe in the next slide or soon. Okay. So maybe it's here. I don't know. Okay. So something very, very important. I told you this before, but each non-zero element of the finite field Galois field Q will be a power of the generator, this generator. Okay. How to write the zero? Well, will be this. Again, maybe Gab will not use Q here, but P, because he knows that he can embed some finite fields into other finite fields, and this is very useful. This is how you write the zero of this particular field. You cannot use only the zero, because it will not work. And you can also use the function zero. Okay? And how to write the 1? Well, you can use 1 of this field, and it returns the number 1. This is multiplicative neutral element, yeah, or just to the power 0, right? This is another way of representing the number 1. So you see, this element is the same as this. 0 belongs to GF4, of course not. This is a rational number. This is not related to rational numbers. 0 of rationals is this. 1 of this is this. Is 1 here? Of course not. Right? 1 of the rationals is this. So these are different things, and God cannot mix them. Okay. I mean, it's not so bad. It's just that you need to know this in advance, otherwise you will make mistakes. Okay. Good. So this is what you wanted to know. So in some cases, you can recognize the elements, right? Say that I have a finite field with 5 elements. So I know that these are the elements. So I take a fifth primitive root of 1, and then I know how to generate all the elements, right? Well, but I can, in this particular case, I can just convert them into integers, right? Because, well, here it will work. So, for example, if I just convert to an integer this power, of course, the answer should be 1. It is. This, what is this? Which number is this? We don't know. God knows. Okay, it's 2. God knows. We cannot recognize the 2, but God knows that this is number 2. How can you, what is this? Of course, this should be 4, because this was 2, and this is 3. Okay? It doesn't make sense to try to do this for GF4, right? Because this is different. Right? You have a different representation, but for this case, it is okay. Int is a function to convert something into an integer. And, well, God knows what you're trying to do if you apply this to this. And it does what you are waiting for, okay? An exercise, again, on permutation polynomials. So I don't know if you know what is a permutation polynomial, but this is a very old stuff. Oh, sorry, I found another typo here. This is the integers. So permutation polynomial is just a function from a ring to the same ring, which is a permutation. Projective. Okay? This is pretty famous. So the exercise is to prove that this map, of course, with GAP, right? Write a computer program to check whether this map is a permutation of this ring, right? And of course, then I want you to write this as a product of disjoint cycles. Okay? Very good. So now let's go to matrices. Do you want to make experiments with finite fields? Yes? Which one? You need to give me the experiment.
Well, is there a way to find the underlying structure of a field, or like when you generate like the cyclic group? Is there a way to present the underlying structure so we know the representative that Jack picked?
That depends on what is precisely what you're looking for. So, oh, sorry. Gab is trying to precisely use. Gab is using this, right? That all the elements are powers of this generator.
Yeah.
What kind of structure you want to find there? You know how to multiply. You know how to
see the generator.
Well, in some cases you can, right?
I can or cannot.
You can, for example, for Galois field of 5 elements, you know which is the generator.
Yeah.
But say that you have GF4, then what is what you want? So you need, if you want to present this as a quotient of a polynomial ring, then you can produce this polynomial ring, check that these two things are isomorphic, and see which kind of element is your generator, right? That depends on you, essentially, because you don't need all the extra information to define this field and to work with it, right? So in principle, if you want to understand this in some other terms, then you need to know what is what you want to find, right? Yes?
So in the last example, you were able to convert to an integer.
Yes.
All the different generators. What if, like, is there any way to convert to an integer interpretation if you're in a non-cyclic group?
We can try, but I think, I mean, I don't know. So I don't know what Gab is going to say. Maybe Gab will answer some crazy thing that we don't understand, which might make sense or not, but we don't know. Or maybe it says what? We can try.
Finite field is not isomorphic to any integer ring.
No, of course, yeah.
So but integers won't really work with that.
But we don't know what is going to happen, right? I mean, you have to be really careful with this because. So let's say, so so this is our generator, right? Say, and I want to see this as an integer. Okay, it's wrong. Okay, which is good. Which is really good. Okay.
Oh, and also previously, when you're demonstrating an experiment, you have z bracket 2 to the power of 2, and they are in the bracket, like 2 to the power of 2.
But this is a ring, right?
Yeah, and then you have another thing, say like z2, and then to the power of 2. Are they the same? Like, do they mean the same thing?
So what do you, so like this? Okay.
Yeah.
This is the same as this, you mean?
No, like z2, and then like you have that thing out of this bracket to the power.
I think in the list of the elements, when you listed the elements in Z4, there was one that was Z2 caret 2, and then with another caret 2. I think that's what Sarah means. I think it's like in the list of the elements for.
In the list of the elements. So okay, let me go back to this. Let's see. Here? No. There. Here? No. There. This?
Yeah.
So this is how he writes the 4. I don't know why, but he writes the 4 like this. Sometimes he's not very clever, I have to say, but this is how he writes the 4, and it is power 2. And so here you don't have the 4 because he wants to have this inclusion, like GF2 included in GF4, which is very, very useful. It's really important to have this inclusion, right? Not to think that these two are completely different. So is this your question or what?
Oh, I just wanted to figure out like why you're writing it this way. Yeah.
I don't know. Why is writing like this and not a 4?
Yeah.
No idea. Really, no idea. Maybe because he wants to, stress that, make a point that here these two and these two that you have, well, they are the same, and you have the inclusion. But I really don't know. Really don't know.
Why don't we look at a bigger power? Think of elements of GF16 and see how it turns out.
Okay, let's go back to the experiments.
So again, like GF4 is embedded and GF2 is embedded, so you'll see some more.
So G, what do you want?
16.
16. Okay, another very useful command is this variable last, which is the last thing you did. So this is how you see GF16. Again, you see several inclusions, right? I think that it's just a matter of trying to recognize the inclusions. That's why he's writing in this way. I don't know if he has a better explanation. I don't know why I'm saying because.
Well, I guess it's always a prime power, and if the number was very large,
Yeah.
you couldn't see which prime it was a power of.
Yeah.
So maybe that's just fine.
But you see here that, well, you see the inclusion, right? 2 inside 4, and 4 inside 8, and 8 inside this of the thing. No, sorry, 2, 4, and 16. Sorry. Okay. Good. So let's go back to. Good. So. Okay, matrices. So how you write a matrix here in GAN? It is just a list of lists. Okay, so this is. So let's say that this is the matrix. Okay, here, what you see here. So the first row is 1, 2, 3, and the second one is 4, 5, 6. Okay, so you write this like this. This is the first row, and this is the second row with square brackets, and then a big square bracket containing everything. Okay. So M is my matrix. I'm not writing the output because it is annoying. I will see precisely this with some spaces. But if I want to have a better presentation of my matrix, I use this function, display. And this in general works with every GAN object. If you use display, then you will have a pretty pretty set. This is the element 1, 1, so it is 1. This is 1, 2, so it is 2. 2, 1 is this 4. And dimensions math will return the number of rows and columns. Okay, 2 rows, 3 columns. Right. So, so let's compute something. Say that B is my vector. This is a vector. Okay, 1, 2, 3, and W is this vector. 0, 5, minus 7. Row vectors of rational numbers. I want to compute this. To see that this is this, I want to compute this. Well, I define my vector. I need to use square brackets, otherwise it will be a permutation. I write this vector. Is a row vector? Yes, of course it is. Is a row vector? Yes, it is. Well, I just compute this, and this is what I get. I compute this. This is what I get. This is useful if you want to prepare, for example, a set of exercises for students. Well, it's useful to use this. Right? If I want to compute an inner product, well, it's just this. He understands that product for 2 row vectors will be the inner product. Okay? A very simple exercise with matrices, well, you need to define these 3 matrices and then compute A to the cube, BC, CB, A plus CB, and 2A minus 5 CB. This is super easy. So here you need to use variables, right? Say A will be this matrix, B will be this matrix, and then you need to do this. It's not hard. So say that you want to construct a null matrix. Well, you have a function for null math, which just returns the null matrix. Okay, 2 columns, 2 rows, 3 columns. The same for constructing the identity. You fix the size and then you have the identity. And if you want to construct a diagonal matrix, well, you just need to use this function, diagonal math, and then what is what you put in the diagonal. Okay? And then you get the diagonal matrix. That's very good. So we know how to get an element from a matrix. This was the kind of comment. But how can you get a submatrix? This is useful sometimes. So let's say that M is my big matrix like this. So 1, 2, 3, 4, 5, 6, well, this, and then some other numbers. Well, what you need to use is this kind of comment, right? This is the matrix, and then rows. This is curly brackets here, and then columns. So for example, M, I'm getting this means from 1 to 3, right? 1, 2, and 3, and the same here, 1, 2, and 3. So I get this matrix, which is okay, right? I'm the first 3 rows and the first 3 columns. Right? This is submatrix. And then I can do this 2, 4, 5, 1, and 3. This is just a comment. So this is how you get a submatrix. I'm doing this because this is it's not easy to find in the manual, right? So that's why I'm doing this now. So of course you can work with matrices with coefficients in arbitrary rings, right? So how can you do that? Say that I have this matrix. I write this. But then I want to think that these are not integers, but elements in the finite field with 5 elements. How can you convert this matrix to a matrix like this? Well, the trick is just to multiply my matrix by the one of this field, and God will understand that all the matrix will live in my field. Okay? So this is how you convert this into this, which is the same thing. Because if you just do display, then you see something pretty nice. Okay? And of course, you don't need a 5 here, right? You can put a 7 or something. But if you, of course, if you have a different thing which is not prime, then you need to think a little bit more about how to do this. Okay?
Is there any reason that zeros get displayed as dots?
So here you mean?
Yes.
It's nicer for printing.
Oh, I see. Yeah. Especially if you have a sparse matrix.
Yeah, exactly. Yeah. You see some dots, and it is pretty nice. Not to see the zeros. The same example as before, but now my coefficients will belong to this ring, set mod 4, but not a field with 4 elements, but this ring, which is not a field. Okay. So M is the identity matrix, 3 by 3 an identity matrix, but with coefficients in this ring. And then I print, and this is what I get. And here, he doesn't know how to write this in a better way. I don't know why, but he writes the matrix like this, and then he writes this particular line, right? Stressing that we are just working over this field.
So,
yes.
In the last example, oh, never mind. Sorry, we're not in Z4 as finite field. We're in Z4 group. Okay, never mind.
Okay.
We're fine.
So, as I said before, what if you want to compute the inverse of a matrix, a square invertible matrix? Well, you just use inverse, right? So this is my matrix, this is how I compute the inverse, this is the inverse. And if my matrix is not invertible, then I get some kind of problem. I get a failure, okay? If you want to check, for example, if a matrix is the identity or not, because this could be kind of hard to check, right? You have a function which is identity math. So again, right, this is like the rule. If you want to check something, well, you start with is, and then try to guess what to put next, and then you look into the help, and well, you will find what you're looking for. This function will return true if you have an invertible matrix, and false always, right? For example, here, I have my M, which is invertible. I compute the inverse. I multiply these two. Sorry, I said the invertible one is the identity, right? Sorry. This is the identity because, well, this matrix is invertible. So, of course, you can compute the determinant, of course, right? But this is it. Say that I want to compute the transpose of a matrix. Of course, this is just a function. Okay? And again, for matrices, the rule is that you put that at the end. There are other small rules that you will learn about, like being computing this in a naive way or just in a better way, but this is not important. Okay, so with this you compute the transpose, and I have this exercise. So it's a silly exercise, but tricky. So I have a matrix, this matrix, which is not a super interesting matrix, with rational coefficients, and I want you to compute the eigenvalues and eigenvectors of this matrix. What is the problem? I mean, it's pretty clear that if you just search for this function, you will find eigenvalue as a function and eigenvector as a function. The problem, again, is that gap is acting on the right. Remember that, right? So, eigenvectors like this returns generators of the eigenspaces, where V, a non-zero V, is an eigenvector of A with eigenvalue lambda if and only if this is happening, right? Because matrices are acting on the right. Because gap is acting on the right. This is interesting, right? I mean, You can compute the kernel of a matrix, you can compute eigenvalues, eigenvectors, whatever you want, but in this way. So you are not using column vectors, but row vectors, and you are acting on the in the dual space, right? You're acting on the right. So if you really want to do this in the classical way we do this, just acting on the left with column vectors, you need to transpose this in a clever way, right? You need to rewrite your functions to get what you want, which is essentially the same thing, but it is important to know this, okay? Yes?
This might be a question for later this week, but how does the matrices work with polynomials? So for example, I know in, I believe in Mathematica, if you have like x plus 1 and then input a matrix as your x, it'll add the matrix of all ones to.
Yes.
And not understand it as the eigenvalue.
Well, you can define matrices over rings. So first you need to define the ring. So with the base, I don't know. So say you want a polynomial ring. So you need to define the ring, which with the variables, which variables, and then you need to define your matrix over this ring. Similar to what we did, right? But you need to define your ring. So you need to define your ring, for example, with 1, and then you create your matrix and try to multiply by the 1 of this ring, for example, if this is going to work.
My problem was more that like if you just put in a polynomial in Mathematica, like x plus 1 or x plus 2, then if you input a matrix as your x, then that plus 2 at the end will add the matrix also.
Ah, yeah. You mean this 2 times the identity? I don't think God will do this automatically. No, you need to do it yourself. I'm pretty sure. I don't know, but yes.
This particular matrix is in the rational numbers.
Yeah.
But when you compute the eigenvectors and eigenvalues, they're not going to be rationals.
Of course.
So how does GAP know which ring to
No,
be?
it will. No. It doesn't. I think that it will return only those that he can return.
Oh.
Okay. Yeah.
So he will try to work in the rational numbers?
Yeah. I think so. I think so. I'm not completely sure, but I think yes, because he doesn't know how to work with complex numbers, right? I mean, he knows about cyclotomic extensions, but that's it. So
I see.
In general, yeah, you have to be very, very careful with this. If you want to do some numerical linear algebra, GAP is not for this. You need to use a different software.
So it might work in the appropriate ring extension.
Exactly. Yeah. Yes. And you want to answer
something?
Okay. Yeah. No. Yes. This is. So if I don't remember how it works for finding, the roots of the characteristic polynomials, but I remember having seen that, for example, you will not get all the roots, right? So maybe he can factor something at some point, and then he returns some roots, and that's it. Oh, it's time? Okay, let me see. Okay, so okay, I have more stuff, but tomorrow I will continue. Okay, thank you.